My name is Faith Johnson, and today I will be going over Feudal Steering, Hierarchical Learning for Steering Angle Prediction. In this work, we use feudal networks for steering angle prediction. The basis of this method comes from hierarchical reinforcement learning, where there's a network hierarchy based on temporal abstraction. We test our network performance on the Udacity dataset, which provides egocentric dashcam images paired with steering angles for a vehicle as it navigates through a diverse set of driving tasks. We show our predictions, shown here in orange, compared to the ground truth angle, shown in blue, on their corresponding frames from the Udacity dataset. We demonstrate that our network is capable of handling more extreme driving scenarios, such as making sharp turns, as well as more mundane driving scenarios, such as simply going straight or navigating in high traffic situations. We achieve steering angle predictions within 2.67 degrees of the ground truth angles. To do this, we create a network broken into two parts, a manager network and a worker network. The manager network operates at a lower temporal and spatial resolution than the worker network. It takes in a series of historical predicted steering angles and produces a goal vector. This goal vector encapsulates the temporally abstracted action of the vehicle, which we call a subroutine. The worker network operates at a higher temporal resolution and uses this goal subroutine vector to add more context and guide its predictions. Along with the goal vector, it takes in a sequence of dashcam images along with the previous predicted steering angle and predicts the next steering angle for the vehicle. This manager-worker relationship allows the network to break down the steering angle problem into more tractable pieces. The makeup of our manager and worker networks is similar, so we only show a breakdown of the worker network. We first pass the sequence of images through 4 convolutional layers. Then we combine the intermediary representations to get one feature vector. We pass this feature vector through an LSTM with the goal vector from the manager. The output is then passed through some fully connected layers to produce the steering angle. We use TSNE to plot the predicted goal subroutine vectors from the manager. Notice that the subroutines naturally form clusters that exhibit similar driving behaviors. We also include frames from a selection of the clusters to illustrate the corresponding vehicle behavior. Starting from the top left of the scatter plot, we see that the vehicle is making sharp left turns. As we move down to the middle of the graph, the turns become less and less sharp until the vehicle is going straight on the road. Then, moving down to the bottom right-hand corner, this straight driving behavior becomes more and more curved until the vehicle is making sharp right turns. We also verify that the subroutine clusters show the vehicle exhibiting the same behaviors. In the graph on the right, we show a subset of frames from the scatter plot in the left column. Each row contains frames from neighboring points in the corresponding subroutine clusters. Notice that each row exhibits very similar behavior. From this, we show that our network has learned the underlying subroutines in the Udacity data. Using the predicted subroutines from the manager network, the worker network predicts the steering angle of the vehicle. The graph on the left shows a comparison of the ground truth steering angle in blue juxtaposed with the predicted steering angle in orange for a portion of the Udacity data. Notice that the prediction follows the ground truth very closely. The graph on the right shows the corresponding predicted subroutine ID. Notice that it shows distinct values for different behaviors on a continuous scale. We compare our method to 5 others, of which our predictions outperform 4. Our method differs from them first and foremost by using the feudal network approach, and secondly, by learning the subroutines in the data instead of predefining them. And, additionally, we allow these subroutines to be continuous instead of discrete. The 5th work we use for a comparison uses a complicated network that simultaneously uses the optical flow and the semantic segmentation representation of the scene in order to make its steering angle predictions. Our approach may be better, especially in mobile implementations where cost and energy efficiency are issues.